For lesson 7, we are going to compare functions. So last week we learned what a function was, and we spent a lot of time discussing that functions don't have x values that repeat. So now we're going to look at different functions and compare them. So you have learned to identify a function. Take a look at this problem. Today was a snow day. Felicia decided to track the snowfall. There were already 2 inches of snow on the ground from a previous storm. Felicia measured the snow from today's storm at the end of each hour. She found that exactly 1.5 inches of snow fell each hour. If it snowed at this rate for 5 hours, how much snow was on the ground at the end of each hour? Use math you already know to solve the problem. So it said that 1.5 inches of snow fell every hour. So there's already 2 inches on the ground. So that's why 0 is 2, because that's when it started. They already had 2 inches. They got another 1.5 inches in the first hour. So that would make a total of 3.5 inches. Another 1.5 inches for the next hour would be 5, then 6.5, then 8, and then 9.5. So let's use that to answer these questions. It says in the table, 0 represents the time when the storm had started. How much snow was on the ground then? Well, they told us 2 inches. How much snow fell in the first hour? They told us that 1.5 inches or 1.5 inches fell every hour, so 1.5 inches. So how much snow was on the ground when Felicia measured it at the end of the first hour? There was 3.5 inches of snow. How you got your answer, you took the 2 that was already on the ground and we added 1.5 inches. Describe how you can use addition to find the depth of the snow at the end of each hour, then complete the table. So we've already completed the table and we are just going to say that we added 1.5 to the previous total. D, suppose you multiply each hour in the table by the rate of 1.5 inches per hour. What else do you have to do to find the total depth of the snow? So if we go back up and look, they're telling us to take the hour and multiply it by 1.5. So if I take 1 and multiply it by 1.5, I would get 1.5. If I took 2 and multiplied it by 1.5, I would get 3. 3 times 1.5 would be 4.5. 4 times 1.5 would be 6, and 5 times 1.5 would be 7.5. So they're asking you, what else would you have to do to that answer to get the actual correct number? Well, that would be, we would have to add 2 to it because there was already those 2 inches of snow on the ground. And write an equation for this situation. Let S represent the depth of snow in inches and H represent the hour. So S is going to equal, the amount of snow will equal 1.5 times the hour, whatever hour we're on in that snowstorm. And then we have to add that extra 2 inches that was already on the ground. All right, you are familiar with proportional relationships that start at 0, 0. For example, 0 hours worked means $0 earned. The problem on the previous page does not include 0, 0. The problem states that there were already 2 inches of snow on the ground at 0 hours. This function starts at 0, 2, so the initial value or the starting output value is 2. So initial value is a vocab word. And that is just where does it start at? So let's look at the graph. So they've already graphed this for us. And it started with the 2 inches on the ground. So that's why our y-intercept, our y-axis there is starting at 2. And then if you move over 1 hour, and then you would have to go up 1.5 because that is how much snow fell in 1 hour. So Every time you go over an hour, you have to go up 1.5 to get to the next dot. This graph also shows the rate of change, and that rate of change was going over an hour and up 1.5 inches. The x values and y values change at different rates, but the ratio of these changes is always the same. From point to point, the y values change by 1.5, so it means we go up 1.5 every time, and the x values change by 1 unit, so that represents our 1 hour. We went over 1 hour every time. So the rate of change is 1.5 over 1, or which reduces down to 1.5. You will discover later on in this lesson that functions can have many different initial values and rates of change. So reflect. Dora opened a savings account and deposited $50. When she gets her paycheck each week, Dora will put $25 into the savings account. Describe the initial value and the rate of change for this situation. So the initial value is what she started with. And it says she deposited $50. So the initial value is 50. And then what is the rate of change? And that is, what are we changing by every week? Well, she's putting in $25, so we're going to add $25 every week. So rate of change is really 25 over 1, so $25 per 1 week. We're going to interpret and compare rates of change. So for this example, a biologist studied the growth of 2 different trees over a 5-year period. At the beginning of the study, she measured each tree's diameter. The biologist took the same measurement each year to determine the growth. The red maple in her study had a starting diameter of 4 inches. The diameter grew at an average rate of 0.3 of an inch per year. The graph on the right shows the growth of the silver maple tree. Which function had a greater rate of change? So if I zoom in on this graph here for the silver maple, this dot right here is its initial value. So it looks like it was 3 inches in initial the first time that she measured it. And then I'm going to look at this point over here because I can tell that that lands exactly on the ordered pair to 4. That's why I'm not going to pick this point here in the middle, because it's somewhere in the middle and I have to estimate where it's at. I'm not sure, so I'm going to go with that point that I know exactly where it ends. So I'm going to go up and then I'm going to go over. So this dot right here, the starting initial value at 3, is right in the middle. So I have to go up to 4. So I'm going to go up 1. And then I have to go over to get to this dot. And if I look at the x-axis there, it's going by 1s. So that means I went over 2. So my y change, it goes on the top. So that's called a rise. And then I move over, my x change, the x value change was a 2. That's called the run, because you run side to side, you rise up and down. So I would have 1/2, and if I wrote that as a decimal, 1/2 is the same thing as 0.5. So if we look back at the red maple, it said that it grew at 0.3 of an inch per year. I just read from this graph that the silver maple grows 0.5 of an inch per year. All right. So make a table of the values at the beginning of the study, year 0. The diameter of the red maple tree is 4 inches. Its diameter grows by 0.3 of an inch each year. So that just add 0.3 on there to fill in the rest of the table. Use the values in the table to make a graph. So then they graphed those points from the table here. And then down here, write ordered pairs for the points that show the initial values on the graph. So the initial value is that starting point. So the red maple starts at 4. And the ordered pair for that point would be over 0, up 4. So for the red maple, we can put, there we go. Oh goodness. 0.04. And the silver maple, if I go back up, it started at 3, so that ordered pair would be 0.3. What do the initial values represent in this problem? And if you remember from the problem, it said that the starting diameter was 4 inches for the red maple. And we decided that from the graph, the starting diameter of the silver was 3. So it's the starting diameter of each tree. Fill in the blanks to describe the rate of change for both functions. So the red maple went up 0.3 for every year. So we're going to put 1 year underneath of that. And the silver maple, we decided grew 0.5 per year. So it would be 0.5 for every year. What do the rates of change represent in the problem? And that would be its growth per year. How much did it grow each year? And which function has the greater rate of change? And that would mean that would be the silver maple. 0.5 is bigger than 0.3. And what does that mean in this context? And we can say it just means that this tree is growing faster. Grows more per year. All right, try it here. Use what you just learned to solve this problem. The table and the graph show how much money a store earns selling each team t-shirt and each team cap. Compare the rates of change for these two functions. So if we look, the number of t-shirts sold in this table, we're going up by ones, and looks like the pattern here is adding 4. So we can say that the rate of change for the t-shirts is $4 per shirt. And the hats, we are going up to, amount earned. I guess I didn't read that chart. It's how much they're making per hat. And over 1. So up to and over 1. And it says amount earned on the side. So they made $2. And we went over for the number of caps. So the caps, they are making $2 per cap. So definitely making more money off of the t-shirts here.